Hello all, welcome to the first video of section 4.5. We'll open with a theorem. If a vector space V has a basis of n vectors, then any set of vectors in V containing more than n vectors must be linearly dependent. And the idea here is that, theorem 1.8 says that an Rn, any set of more than n vectors, is linearly dependent. And the idea is just that, well, as soon as we pick coordinates from V, it's indistinguishable from Rn, basically. So it says any set of P bigger than n vectors in Rn. Let's move this over here. Give ourselves some more space. In Rn must be linearly dependent. And then the last section we saw last time we saw the coordinate transformation makes V, and once we fix coordinates on V, it's essentially indistinguishable from Rn. Last time we saw once we fix coordinates on V, is indistinguishable. Indistinguishable from Rn. But this is a big caveat, right? I mean, fixing coordinates is a thing. There's a bunch of different ways you can fix coordinates. So it isn't just like every vector space is Rn. It's any vector space with coordinates looks just like Rn. Okay, and we'll hit you with another theorem. If a vector space V has a basis of n vectors, then every basis of V has exactly n vectors. What's the idea here? So if we have more than n vectors, 4.9 says those vectors are linearly dependent. If we had a basis of fewer than n vectors, then 4.9 would say that this basis of n vectors is linearly dependent, but we know it isn't. So that can't work. If we had a basis of fewer than n vectors, 4.9 says our original basis is linearly dependent, which we know it isn't. We know it isn't because a basis by definition is linearly independent and spans the entire vector space. Okay. And of course, you can see more details for these theorems in the textbook. I just wanted to give you an idea of what the proof sort of contains. Okay, definition. If V is spanned by a finite set of vectors, which is most of the vector spaces that we've been talking about, if V is spanned by a finite set of vectors, I would say V is finite dimensional. Oh, defining that. And the dimension of V, dim V, that's how we write it, is just the number of vectors in any basis. Otherwise, we say that V is infinite dimensional. I don't think we're going to say much about infinite dimensional vector spaces in this class. If you are curious about infinite dimensional vector spaces, there's a graduate class in functional analysis somewhere for you. Okay, let's do an example to make this more concrete. Let's let H be the set of all vectors in R3 with the property that x1 plus 2x2 minus 4x3 is equal to 0. We'll find a basis for H. So if x is in H, what do we know? X looks like x1, x2, x3. And actually, we can just solve for x1 here. And so really, it's equal to minus 2x2 plus x3. And we've got our x2 and x3, which are hanging out. And so we're getting what? This looks like it's x2, negative 2, 1, 0, plus x3, 4, 0, 1. Okay, and since we've got a 0 in the third spot for the first vector and a 0 for the second spot in the second vector, these two vectors are going to be linearly independent. Right? There's no way one is a multiple of the other. And we know for two vectors, that's the test for linear dependence. So we can see, yeah, since negative 2, 1, 0 is not a multiple, k times some, whichever one for any scalar. Okay, these vectors are linearly independent. But also, we just showed everything in H is some multiple of the two of them. So it spans. And also, we also know, just saw, if X is in H, X is in the span of these two vectors. But that means that this set is a basis. The basis for H. Which means, oops, we're almost running out of space here, the dimension of H in particular is 2. Right. So if someone else comes along and wants to find a different basis, they're free to do so. And they will find some other pair of vectors that form a basis for this set. There's no coming around and finding 3 vectors that are in H that span and are linearly independent. There's no finding a single vector in H that spans and is linearly independent. All you're going to do is find some pair of vectors always. That forms a basis for H. Okay, maybe we don't need the exclamation point. That seems unnecessary. All right, let's do another example. Let's let P4 be the set of real polynomials of degree no more than 4. So here I just mean real coefficients. The coefficients of the polynomials can be any real number. We want to determine the dimension of the subspace H, which are all the polynomials in P4, such that they've got a 0 at 1 and a 0, or root at 1 or root at -1. Okay, so I'll leave it to you to check that, in fact, H is a subspace, but it is. Maybe let's take a look at let's first get the dimension of P4. So notice maybe 1x up to x to the 4 is a basis for P sub 4. And this means that the dimension of P4 is 5, right? We got 4 right there, and then also one more is 5. Okay. So let's let maybe, P of x be in H. Oops. X be in H. We know that, so then by definition, P of x looks like a0 plus a1x plus a2x squared plus a3x cubed plus finally a4 x to the 4. We also know, since it's in H, that P of 1, which is a0 plus a1 plus a2 plus a3 plus a4 is equal to 0. And we know that P of -1, which is a0 minus a1 plus a2 minus a3 plus a4 is also 0. And one thing we can notice is that this actually gives us a system of equations to solve in the variables, in these a variables. Oops. Okay, so then let's do exactly that. This is going to give us the 2x5 matrix. What? 1, 2, 3, 4, 5. 1, -1, 1, -1, 1, and 0, 0. Sure. Okay, and it'll let you row reduce this, and you're going to get exactly what you think. 1, 0, 1, 0, 1, 0. 0, 1, 0, 1, 0, 0. Okay, so this is giving us what? That a naught is equal to negative a2 minus a4, and a1 is just negative a3. Okay, so then what does p of x look like if a naught is secretly determined already by the other coefficients, and so is a1? Well, this means that p of x looks like, yeah, minus a2 minus a4. That's our a naught. And then our a1x is secretly minus a3x, and then plus a2x squared plus a3x cubed plus a4x to the fourth. And well, we can since we're thinking of the a's as the variables here, those are the ones that determine what the polynomial does. Let's regroup in terms of the a's. So where are we going to find an a2? We've got an a2 with a coefficient of -1 and also a positive x squared. So this is -1 plus x squared. Where do we get a3s? We've got a3 with a -1 and a positive x cubed. Sorry, a negative x. Negative x and a positive x cubed. Minus x plus x cubed. And a to the fourth is going to appear where? A minus a to the fourth and a plus a to the fourth, a sub 4x to the fourth. So this is -1 plus x to the fourth. And what this is telling us is that h is actually equal to the span of these three polynomials. Yeah. -1 plus x squared, negative x plus x cubed, -1 plus x to the fourth. Okay, and we can check these polynomials are linearly independent. And so in fact, so they form a basis. And what? And the dimension of h here is 3. Oops. Okay. I'll see you in a sec for the second video for section 4.5. Take care, everybody.